next talk, and that will be by Stephan Bauer, and he will talk about progress of PTB's 4-terminal per impedance bridge within the GIQS project. So.
Yeah, so I have the honor to present you the progress on PTB's 4-terminal pair Josephson Impedance Bridge within the GIQS project. In contrast to the title, I will focus a bit more on the work which is going on in the GIQS project, because we are now in a very interesting phase of the project. So, as you all know, the GIQS project is an Euromed project, so a joint research project, and duration is as standard 3 years, and we are 2 years have passed already, and we are just in the last year. The consortium is made up of 11 partners out of 9 countries all over the world, as you can see, mainly Europe, but we have also from the eastern part we have KRISS, and we have NIMT, so Korea and Thailand are also with us. Yeah, the project goals. So we want to realize the impedance units in the revised SI. So we want to trace them back to fundamental constant like the electron charge and Planck's constant. Further, we want to shorten the traceability chain, so the primary traceability chain. We want to have easy available primary impedance standards, especially for smaller NMIs and calibration centers, and in future, so talking about maybe years or 10 years, 20 years, that will also be possible at industry. So therefore, we want to fabricate robust graphene devices, so robust QHRs, and we also want to develop different cryo systems to run the quantum Hall resistance. And one part is also the all-in-one operation, so that means that we can operate a Josephson system together with a quantum Hall and one cryo system. And last but not least, so the knowledge transfer between NMIs is one major part, especially knowledge transfer to NMIs which want to start new with impedance measurements, Josephson impedance bridges or quantum Hall systems, to get the knowledge out in the world we gain in our project. So one focus, if I have to pick out one topic, I would say it's shortening of the primary traceability chain, and I will show you a bit more later on in the talk. We implement our project goals. So the first part, for sure, we need easy to use quantum standards to have a quantum impedance standard. So this is the fabrication of graphene-based quantum Hall devices. To realize impedances or impedance units, we need also highly accurate impedance bridges. So we also want to further develop existing bridges, and we focus on digital sources and Josephson sources. So both parts are fully digital impedance bridges. Then we want to combine the further developed bridges together with the graphene-based quantum Hall, and we develop our cryo systems. So it's just an extra part, on the one hand for the quantum Hall operation in AC, and the other hand the Josephson voltage standard combined system. So the first part, our graphene quantum Hall devices. So we want to replace the gallium arsenide ones by graphene. This is done at 3 partners in our project. So first one is PTB, then we have also KRISS, and from France we have CNRS. All 3 institutes are able to fabricate graphene and also make devices out of this graphene. So the idea to use graphene is for sure that we can run it on higher temperatures, so 4 Kelvin. Even though this is possible with gallium arsenide, as shown by a publication of Jan Kuchera et al. I guess graphene is still a bit more convenient to run it at 4 Kelvin. We can run it at lower magnetic fields, so fields below 7 Tesla, magnets get quite cheap. So if you run at 15 Tesla a system, the magnet is a quite expensive part of your system, and for lower fields, you can save a lot of money and make it more easy to operate. So if you want to have more details on the graphene devices, quantum Hall for metrology applications, I would kindly invite you to the talk of Matthias Kruskopf. Oh, it's a typo there, it's Matthias Kruskopf. you will see tomorrow. So to make it a bit more visible, the advantage between graphene devices and gallium arsenide, on the left hand you see the plateau of the graphene device. You can see that we have a broad plateau where we can operate the device, and for the gallium arsenide the plateau is smaller, and the region of interest to having 12K9 is typically in the range of about 8 to 10 Tesla, maybe more, maybe less, depending a bit on the device. And we want to tune the graphene device to fields as low as possible, but not too low that we have a well quantized operation, but this you will also get from the talk of Matthias. Second part, so we want to develop or further develop highly accurate and flexible bridges. So this is a simplified setup in contrast to the IVD bridges. And we can rather simple automate these bridges, which is also a good advantage. The goal is to have fully digital bridges or Josephson-based impedance bridges. And for this Josephson impedance bridges, as Ralph already mentioned, we will use the Josephson arbitrary waveform generator. So we want to make use of the AC capabilities of pulse-driven Josephson arrays. But also digitally assisted 4-terminal pair bridge will be used for R2R or C2C comparisons for a broad range of capacitance values and also for a broad frequency range. So an example of the impedance which you can see on the right, which is the version of INRIM, and this is the schematic. Here you can look how it's look in reality with the computer control, the digital sources, the impedance standards, and the bridge circuit, the detector you need. And here on the lower part, there's Josephson arbitrary waveform synthesizer chip shown, which is made at PTB. And as you can see, there are a lot of publications ongoing in the last years, and these are for sure not all of them, but the most recent covering this topic. So to get a bit the focus on our impedance bridge, so within the project we also further develop our impedance bridge. Before we had a 2-terminal pair definition. Now we use a 4-terminal pair definition. That means that we have a potential definition and a current definition, and with the current source here, we assure that the current within the potential line is 0, or at least is 0 at one point. So for AC you cannot achieve a 0 current through all the lines. Then we have 2 impedances, we have 2 detectors, and if we balance our bridge in the way that the difference between both detectors is as small as possible, which we can assure by this inject a voltage here to take care for different cablings at the low side, and to see that the average of both is as close as possible to 0, or in the ideal case 0. We have a simple equation that the impedance ratio is exactly the same as the voltage ratio, which is now on a quantum-based definition. This is what's looked in reality. You can see our system here. It's the liquid helium duo with the dipstick inside. We have the output of 2 Josephson arrays, a pulse pattern generator, and some arbitrary function generators for compensation, which is needed for the Josephson system, and some detectors and more electronic. And the right picture shows you the impedance standards with an amplifier, the detectors, the 2, like you see here. We see all these current injection and current detection, which is essentially this part here, and also the Kelvin injection, which is here, and some active equalizers, but I won't go into the detail of that. So the Josephson arbitrary waveform synthesizer, which was introduced by Sam Benz and colleagues, delivers a high spectral purity. We have infinite stability due to the quantum definition of this voltage, and we have a very high resolution. In our system, as you see the chip here, we have 2 independent voltages. We can run up to 100 millivolt. You see the half of a chip I presented you before here, and the other one is underneath these copper capsule, so that we have a very good screening between both sides, or between both voltages, to keep them as independent as possible. I will show you later how much the crosstalk is. And you we can set the phase angle between both voltage by shift of the starting point of the both codes we load in our pulse pattern generator. So the phase angle can be set very accurate and very reproducibility by these pulse generators without changing some synchronization or something else. And you can see in this picture that the spectral purity is only limited by the spectrum analyzer, which is indicated by the black line here. So now to show you some results which we already measured with our 4-terminal pair impedance bridge, or mainly Joy Pimsu did here at PTB. So the first plot is 10 nanofarad to 10 nanofarad ratio over the frequency. So we measure from 50 Hertz about to 50 kilohertz. And you can see that we have some kind of slope here. So we have a frequency dependence, but we compared with the IBD bridge of Jürgen Schur, as you can see here by the green triangles. And the agreement is, for example, at the 1 kilohertz range is in the order of some PTBs, so about 2 nanofarad per farad, and for around 5 kilohertz we have a deviation of about 2 parts in 10 to the 8. But so this is a preliminary result. It's only the type A uncertainties shown. We do not have a full systematic evaluation of our uncertainties yet, but we are working on this. We also made comparison of resistance standards. So this is the ratio of 12K9 resistor compared to a 10 kilo ohm resistor. And you see that we have a quite linear slope in frequency. And the red triangle here shows a recent result of the cryogenic current comparator bridge running, which is operated by Martin Götz. And also here the agreement is quite well. To test other devices, we also used two 10 kilo ohm resistors, which are now a couple of years old and have a very low drift. You see a slight different frequency dependence, but also here we have comparison to the CCC bridge of Martin Götz, which is quite well, and also we started to compare those values to the PJVS impedance bridge, so with programmable Josephson arrays. So coming to the next part, which is the cryo systems, all our partners made great success on their individual systems. So we have at almost every institute which wants to run a quantum Hall system, they are ready. We have different systems, so different adapters to have the TO8 comparable to AC measurements. The LME has a 2x2 holder, as PTB also did. CMI developed a new TO8 AC holder system, and also made the first version of the AC dipstick with the knowledge from INRIM, which uses a commercial 6 Tesla magnet, which can go into a storage dewar, with also a TO8 holder with AC cabling. The knowledge of INRIM and CMI was transferred to KRISS, which made also a very nice version of this AC capable holder. And at RISE in Sweden and VTT in Finland, the progress is made on operating quantum Hall system together with the Josephson system inside one cryostart. So both are pulse type cryo coolers. So the one is a commercial solution, and the other one is a homebrew. So you can see that we have different approaches which lead to the same idea to operate Josephson standards and quantum Hall next to each other, which is a great challenge, and we will see how it will work. So after having all these cryo stuff running, and we can operate a quantum Hall at low fields and liquid helium temperatures, we now need to look at the combination of our impedance bridges and also the graphene-based quantum Hall device. So the steps up to now is typically IBD bridges are used, which is the most precise way to measure impedances, but the complex traceability chain maybe introduce additional errors, but up to now there's no other possibility. You can rather start from a DC world with the a quantum Hall and a cryogenic current comparator using AC-DC transfer, and then a quadrature bridge to transfer the resistance to capacitance, and then you go with a 10-to-1 bridge to the desired 10 picofarad, which is the workhorse in impedance calibration. The other way around, you can also start from AC with the Thomson-Lambert capacitor and then going all the other way around, which is also a good but challenging way. So the first idea is to look into the AC part, starting with the AC quantum Hall and transferring this to a capacitance via a quadrature bridge, which is running right now by Jürgen Schur, and then again going by 10-to-1 IVD bridges to a 10 picofarad system. Now let's look. I mentioned my favorite implementation is the shortening of the traceability chain. Right now in AC with IVD bridges, you'll see a traceability chain like this. You need a double bridge, so two capacitors, two quantum Hall resistances to get the 10 nanofarad value out of the quantized resistance. So with a Josephson or any other digital impedance switch, you can shorten this because you can easily create a phase shift of 90 degrees, which is needed to transfer the quantum Hall value to the capacitance value. And then you can just use your established 10-to-1 calibration ratio to go to the 10 picofarad. So this is already a simplification, and it can be easily automated, the system. A further step, which was already introduced by Metas, I think Blaise, Frederick, and I discussed at the last DC&QM meeting I attended in Espoo a couple of years ago, just to use a 10-to-1 quadrature bridge to running the quantum Hall and directly to a 1 nanofarad instead of 10 nanofarad, and then you can just shorten this even further, and Metas was also able to use 10-to-1 Josephson bridge to go to the 10 picofarad, which shows very good results, even though it's not yet with the quantum Hall device, but with a reference resistance. But this is quite promising that you can shorten the traceability chain quite a lot. So to show you how we do a dedicated impedance bridge at PTB for the quantum Hall measurements, we do in principle the same as I showed you before in the ratio bridge. So we have two Josephson voltage standards giving us the voltage definition. Then we provide a current by some arbitrary source, which is simplified here now, and we will detect a value, and if everything is balanced well, we have the well-known easy equation that the impedance ratios equals the voltage ratio. And we have a special advantage for the quantum Hall, which lays on the triple series connection, which all of you know already. So we extend our bridge from 2-terminal to 4-terminal pair definition. So we had already made measurements with the quantum Hall and the 2-terminal pair. Now we have the same. We have the voltage definition, the current definition, and we just provide a current, which is then detected by current detectors in the potential line. And the great advantage is now, due to the triple series connection of the quantum Hall, we have the great opportunity to have a zero current at our potential low line already, which is ensured by the triple series connection here. So as I showed you before, we had the Kelvin injection to circumvent the inequalities at the current low lines, which is no longer needed for this bridge setup. So this simplifies quite a lot. Nevertheless, we have to take into account cable corrections, which are different for a quantum Hall triple series connections or a 4-terminal pair definition. But yeah, this is future work to evaluate this quite precisely. And I will show you now some first measurements we already made. So we use 4-terminal pair standards and a 2-stage thermostat, and they are stabilized in the millikelvin range. And if you now look at the Allen plot, so we see the Allen deviation in nanovolt over the measurement time, or if you like relative units, you can also see at the right scale the relative unit, and we just measured a 10 nanofarad capacitor versus a quantum Hall resistance, which was this time provided by the colleagues from NIST. And you see that the measurement itself just followed the theoretical expectation of noise we have in our system. And so our minimum type A uncertainty is, after about 3 minutes of measurement time, is 2 parts in 10 to the 9, which is quite good, I guess. So typically we just shorten a bit and we end up with 3 parts in 10 to the 9. And this we also made for a resistance standard. So we traced our 12K9 reference resistor made from single Vishay chips compared to the quantum Hall, again the NIST sample. And you see that also here the fitted Allen deviation fits quite well the theoretical expectation. And to see how reproducible our bridge is, we made measurements over a couple of days. So you see here the red dots represents measurements where we traced the resistance to the quantum Hall, and the quantum Hall was traced back to a capacitor which was calibrated by Jürgen Schur. So we use the quantum Hall this time as transfer standard to calibrate the 12K9 resistor over our 10 nanofarad. So it sounds quite complicated and maybe not useful, but we want to see how reproducible and how stable our bridge is. And to compare, we used the stability of the resistance standard measured by the CCC bridge. And you can see that the agreement is quite well. So we have a slight offset, which is due to some systematic effects, but the drift is just the same, essentially. So we are quite sure that we can measure quite reproducible with our impedance bridge, but now we have to evaluate every detail on the systematic contributions. So also other colleagues developed the impedance bridges for combined with quantum Hall. So this resistor can be replaced by a quantum Hall in the near future at the in-rim solution, but also CMI in the Czech Republic and also KRISS made advances in digital bridges for the quantum Hall resistance. You can see the impedance bridge on the right side, the quantum Hall system here in the middle, and the small inset here shows you the DC value of the quantum Hall and also the AC, which has these typically curved shape for AC measurements. Colleagues at METAS made great progress measuring quantum Hall devices against other standards. So you can see the impedance bridge, this time digitally assisted. For the moment, it will be replaced quite soon by the dual Josephson impedance bridge of METAS. And you can see here the quantum Hall resistance is applied here as in the triple series connection. You can see the probe head and also the sample if you just zoom in. The results are quite they're quite well, but this is the great advantage of having many institutes measuring on different samples. You see that out of a sudden here occurs some resonance, which is quite reproducible, and right now the sample was shipped back to PTB, and we are just investigating if this is a problem of the source or feature of the quantum Hall device. This is the great opportunity we have in such a big project to exchange experience, knowledge, and also samples or equipment. Yeah, so if the dual Josephson impedance bridge is ready, this schematic looks quite the same. We have now the JAWS impedance, the JAWS voltage standards to provide the voltage definition or the potential definition, and the quantum Hall also made from graphene. To go a bit more, or just show some pictures of the collaboration and comparison, which is quite well in our project, I can just not often say that, I cannot say it often enough. So KRISS, for example, made the transport container, which was used to ship samples all around the world. You can see that you can have up to 3 samples here. And also PTB made a smaller version of this to transport it under an inert gas to have controlled conditions for the shipment, and how great that works I can also reference to the talk of Matthias tomorrow. And here now you can see a DC comparison of two different samples. So the first one is one made by KRISS, and you can see the DC characteristics, so the quantum Hall resistance and the longitudinal resistance, and that is slightly changing over the measurement campaign. So it was first measured at KRISS, then shipped to PTB, and shipped back to KRISS. So you see that there are still slight changes, but nevertheless you can see that we have great accuracy for the quantum Hall value, and all measurements are in good agreement also. So this is great to have the exchange between labs even all around the world. And a similar thing was made for a sample produced at PTB, and here also we saw shifts in the measurement. Now it was measured at PTB, CMI and Czech Republic, KRISS, and back and forth. But we recognized some change out of a sudden in the sample of the carrier density, and the behavior was changing dramatically. But Matthias will report a bit more of this. So, and now I see my time is already over almost. So to conclude, so we have the vision to use primary standard also at user facilities. That's why we want to realize the impedance unit by means of reliable graphene-based quantum Hall devices. And therefore, we developed impedance bridges and cryo systems, and have the great opportunity in our community to compare and exchange results, to learn from the others, to make recommendations for other NMIs, and maybe also for calibration center. And the wish in the future is to have graphene quantum Hall devices also available at industry. So I want to thank you all for your attention, and also my colleagues at PTB and all within the GIQS project. I just want to mention that there's more information and news on the GIQS homepage, or you can go to LinkedIn, or we have also a YouTube channel. And if you would like to become a stakeholder in our project, I would ask you to get in contact with Luca Caligaro, and so you have no duties being a stakeholder. You will get updates and emails and newsletters from us without any duty. And I think it's not necessary, but I also want to mention that all I presented here was supported by the GIQS project within the Euromet metrology program. So yeah, thank you all.